Good day and welcome back to our first video dealing with lines and planes. And in this video, we will focus our attention purely on lines in three dimensions. Kind of how is it that we should think about them in several different forms that we can write down for their equation. So to begin with, a line is determined by a point on the line and a direction vector, i.e. the direction of the line. And this idea should be somewhat familiar if we think back to kind of our previous experience with lines, maybe in a pre-calculus or algebra course. We typically would define a line to depend upon a y-intercept and a slope, i.e. the slope-intercept form. So the y-intercept would refer to this point that we know, and the slope would be indicating the direction of the line. And it turns out in three dimensions, the idea is very similar. It's just how we formulate the equations that might look a bit different. So to begin, we've sketched a line here that is through a point P naught. And what we would like to do is find an equation that's satisfied by some other arbitrary point P sitting on this line. So I'm going to make just some observations to get us going, and once we have these observations, we should be able to write down an equation of the line. So the first thing I want to note is if we let v be a vector, and it is the direction of the line. And for convenience, I'm just going to call this line L. Then if you take any vector which lies on our line, and a vector that we can very clearly see as being on our line would be the vector going from P naught to P. And because V is the direction of the line, the vector joining P naught and P has to be going in that same direction. And if two vectors have the same direction, what that means is that they are constant multiples of each other. So for some value t, where t is a scalar, t times v would give us that vector. And this is for some t. And let's use this idea to think about how we can maybe get to p from knowing p naught. And I'm going to get there by thinking about vector addition. If we consider the position vector that ends at P naught, let's call that R naught, and another position vector going to P, let's call this vector R. With this observation, we can say that L is characterized by the following equation. If we want to get to R, and we're thinking in terms of vector addition, how we can get there is we can first travel to P naught, and then we can travel from P naught to P. And we indicated previously that we can think of this vector as being TV. So R would be equal to R naught plus T times the direction V. And how we want to think about this is just think in terms of vector addition, as we discussed. And I realize that this is probably a bit abstract looking, so we'll make a few kind of clarifying remarks and then we'll come back to revisit this equation. So the first thing I want to observe to go along with this is that each value of t, and we can really think of t as being a parameter. So each value of the parameter t is going to correspond to a point on the line. But how we get that correspondence, we'll say, is that t gives the position vector of a point on L. And remember, if this is going to be a position vector of some point on L, it's really the terminal point or the tip of the vector that will lie on the line. So the tip of the vector R traces out the line L. So let's go ahead and maybe rewrite this equation of a line in a bit more of a workable form. So first, let's just kind of observe that we know what some of these vectors are. R represents this vector that's a position vector that ends at the point P, kind of an arbitrary point on the line. R naught represents this position vector corresponding to the point we know, x naught, y naught, z naught. And then we have plus t times some direction. So to write down the equation of the line, let's just kind of make a quick note to get going. We are going to be looking for a line through a given point, x naught, y naught, z naught, with a direction vector given as v is a, b, c. So just making it as general as possible. So what we have above is actually what we would refer to as the vector equation of a line. And that vector equation of the line can be written as xyz, so this unknown point on the line, is going to correspond to the point we know plus some multiple t of the direction vector. And this would be the vector equation of the line. And just to make sure it's clear, this is precisely this formula we had above. And then we can take this vector form of a line and we can rewrite it in terms of a parametric and then symmetric equation of a line. And in order to go from the vector equation to the parametric equation, what we can do is note that we have really one vector on the left equaling the sum of two vectors on the right. And if you wanted to even combine those two vectors together on the right, note that this would be equal to x naught plus at, y naught plus bt, and z naught plus ct. So essentially what we did is we took the parameter t, the scalar, and we threw it into each of those components, and then we added them together. And if this xyz on the left is equal to this vector on the right, that means each and every of those corresponding components have to be exactly the same as well. So the first components have to be equal, the second components must be equal, and the third components must be equal. And this is what we refer to as being the parametric equations of the line. And to get from the vector equation to the parametric equation, we simply equate the components of the vectors. And then lastly, we can write down what we would call the symmetric equations of the line. And the idea is to note that this parameter t that we see in each of these separate parametric equations is representing the same quantity. That is, whenever we substitute in the value t into one, we'd substitute the same thing into the others. So note, if I was to solve for t in the first equation, I would have to subtract x naught and divide by a. And if I wanted to solve for t in the second equation, I'd have to subtract y naught and then divide by b. And both of those t's are exactly the same. Similarly, in the third equation, z minus z naught over c. And we think of this as being the symmetric equation of the line, where note, we cut off that t that's not necessary. And I know in the past we're probably used to dealing with, say, a single type of equation for a line, and these look vastly different from each other, but there is something powerful about having, different perspectives or different ways that we can view the equation of a line depending upon the scenario that we find ourselves in. So it is reasonable that we could ask you on an assignment, find the, say, parametric equations of a line. Then, of course, that's what you would want to give as your final answer. Or we could just say find an equation of a line, and you would probably write down the vector equation because that's the starting point. Once you have the vector equation, we go to parametric, we go to symmetric. So let's look at a common example. All right, so to look at an example, let's find the symmetric equation of the line that goes through the point 2 comma 1 comma 0. So remember, for a line, we need two quantities. We need a point and a direction. And the point we have is 2 comma 1 comma 0. And the direction is described as being perpendicular to the vector 1, 1, 0 and 0, 1, 1. So the question is a familiar one. How do we find something which is perpendicular to two given vectors? And hopefully you're thinking back to what we discussed in this previous section 12.4, dealing with cross products. So in order to find V, what we need to do is use the cross product. All right, so we have a point, we need a direction. And if we were meeting kind of face-to-face in class, this is a point where I would be pausing and I would be taking a break from talking, and I would have you all work through this example for 4 or 5 minutes. So this is an ideal scenario to pause the video for a few minutes, see if you can come up with the symmetric equation of the line. And assuming you've done that now, let's go ahead and find our direction vector. We said the direction vector V is going to be perpendicular to both 1, 1, 0 and 0, 1, 1. So the cross product, we would have what? I, J, K across the top row, 1, 1, 0 across the middle, 0, 1, 1 across the bottom row. And if you were to go ahead and calculate this out, remember the pattern plus minus plus as we work across the top row of this matrix, what you would end up with is 1 minus 1, 1. And I'm going to put a dot, dot, dot here just to indicate, there's a small amount of work that I've omitted. And I will certainly do that from time to time at various points in the semester, just so I don't have to bore you with working through all the details. But also let me remind you that being able to perform this computation is still very important. So make sure that if you have any uncertainties or doubts, go through and do those computations, because you certainly will have to do them on, say, a future homework assignments and exams. All right, so we now have the direction vector and the point. So if we work our way through the various equations, the vector equation of the line would be x, y, z, this arbitrary point, is equal to the vector corresponding to the point we know on our line, plus t times the direction vector, 1 minus 1, 1. And we can immediately take the vector equation and convert that into parametric equation. What we need to do is set all of those corresponding components equal to each other. So we think the t is going to be distributed through. And then if we think of the first components, x is equal to 2 plus t. If we think of the middle components, y is equal to 1 minus 1t. And for that third component, z is equal to 0 plus t. And once we have the parametric equation, we can solve for t to get the symmetric equations. So if we isolate t in the first equation, it's x minus 2. If we isolate t in the middle equation, maybe by adding t to both sides and then subtracting y, we would have 1 minus y, which is equal to z. And if we now disregard the t, we are left with what we might think of as the symmetric equation of the line. So that finishes up our discussion of lines, at least for the moment. And I would encourage you all to go to the textbook, look at the suggested problems. Oftentimes when it comes to the difficulty associated with 12.5 problems, it's not necessarily understanding the equations themselves, i.e. knowing we need a point and a direction. It's based upon the context we're given, being able to visualize what's going to represent the point, what's going to represent the direction, and whenever possible, we will try to draw a picture to help with that. So stay tuned for the next video where we'll talk about planes, and take care.